I have phosphorus that has all 8 valence electrons around it with a -3 charge. It's completely fine. But now I have this leftover calcium that has 1 valence electron, and it does not want this at all. And not only does it have 1 valence electron, but now it also has a +1 charge. It needs to get rid of this. So to do that, it has to give this away to another phosphorus. This valence electron is now going to go over here to this phosphorus atom. This now becomes a +2 charge because it lost both of its valence electrons. But let's look at phosphorus now. So now I have only one piece that's messed up because these are all balanced and stable. This is the only piece now. So I have 6 atoms, or 6 valence electrons around this atom, around this phosphorus atom. It needs 2 more to have an octet. If it bonds with 1 more calcium atom or calcium ion, those 2 valence electrons can go right down here to this phosphorus atom, which is exactly what it does. In this case, calcium becomes a +2 charge. Phosphorus becomes completely full with its octet with a -3 charge. So all of these are stable, they're happy, we're good. So this is where we can get C3P2, which you already knew how to write that formula based on what we did yesterday. But what I want you to also understand is how these electrons are moving and how they're transferring, because it's really, really important that you understand that phosphorus needed, this last phosphorus maybe needed 1 more valence electron. So calcium's going to come in again, give it 1 electron, but now calcium has this 1 extra electron. So I really want you to understand that process, okay? For ionic compounds, we also can call them another name. The simplest name or the simplest formula for an ionic compound is called a formula unit. So you may see on a quiz, or you may hear me ask, or for your journal or in your homework, write the formula unit for the following elements, which really just means write the ionic compounds for the following elements. So formula units, ionic compounds mean roughly the same thing. Also, just very quickly, which you already know this, so I think that's why I kind of skipped over it, a chemical formula is just something that can show what elements are present and how many of those elements are present. So a chemical formula can tell us the kinds of elements and also how many elements. So I know that in this formula, I have calcium, so that's a type of element. Phosphorus, it's another type of element. I know also how many of them I have. I have 3 calcium atoms. I have 2 phosphorus atoms. So you already know that, and I'm not worried about that. So just know, though, because this is something new, an ionic compound is also called a formula unit. And specifically, it's just the smallest unit for an ionic compound. All right, guys, we're almost done. I just want to talk a little bit about some properties of ionic compounds very quickly. So in terms of the formula unit or in terms of an ionic compound, formula units or ionic compounds are arranged in something called a lattice arrangement. So this is something called a lattice arrangement. What I would like you to know on this one, well actually I asked this question for you. Which ball, would it be the green color or the blue color, would represent sodium? Because we're going to say that this is a lattice structure of sodium chloride. So based on their sizes, based on the sizes here, I have the green, which is a lot larger than the blue atoms. So if I think about where sodium's located and where chlorine's located on the periodic table, I would get out my periodic table and kind of see, are they in the same group? Are they in the same period? And you would say that they're in the same period. And I know that atomic size, as we move across a row, becomes smaller because that nuclear charge is pulling the electrons in more tightly. So that means if I have to figure out which one of these would be bigger, is it the green one sodium or is the green one chlorine? Because this is the bigger one. So which one do you think that it would be? Would it be sodium or would it be chlorine? Be sodium. So sodium is much larger than chlorine because remember, chlorine is not letting go of those electrons. It has more protons, more nuclear charge to pull in those electrons really tightly. So sodium atoms would be the green little spheres, and then the chlorine atoms would be the blue spheres. So if you look at this picture, you can see this blue chlorine atom is completely surrounded by green. It's completely surrounded by sodium. Think about why that would be. This is negatively charged. It's going to attract all around it positive charges. So this really nice, I think, representation for sodium chloride is a really good way that we can see a lattice arrangement, which simply just means that ions are going to be packed together to form a repeating cycle or a repeating array. So I have, wherever I have a blue, I'm going to have all green around it. Wherever I have a green, I'm going to see that I have all these blue around it. So it just kind of gives us this repeating thing over and over and over again. So it's really just a repeating structure. So this lattice arrangement is also called a crystal lattice. So you can hear them, they're the same thing, a lattice arrangement or a crystal lattice. Typically, ions want to surround themselves, like we already said, with as many ions of opposite charges as they can. So I have the green atom here, which is sodium. It's going to surround itself, or try to surround itself completely by negative charges. Same thing here. I have a negatively charged chlorine here. It's going to try to surround itself as much as possible by as many sodium atoms as it can, which would be the little green spheres or green circles. So there is positive and negative ions that exist in a ratio here. And so we can figure out then, based on this, how many electrons are moving back and forth between these atoms. There's strong interactions here. There's a strong attraction. And there's a really strong attraction between the blue and the green spheres because they're ions, they're charged. So we know that this force of attraction, Coulombic attraction, is really what's keeping this lattice structure together. So ionic compounds form something called a lattice structure, and it looks just like this. We have these repeating units. I have a green, a blue, a green, a blue, a green. So it's just kind of repeating over and over, this structure is. So to go to the next slide is really just what we've just said. Ionic compounds form crystalline structures or crystalline solids, which just means that they show this really nice repeating lattice array or lattice structure. So it says irregular repeating arrangements of ions in the solid. So I know if I have a green atom here, the next one should be a blue. And then I know the next one should be green. And then the next one should be blue. And then the next one should be green. So it's kind of this repeating pattern. Ions are strongly bonded together, which means this force of attraction, this Coulombic attraction, is really holding them in place. The structure is also really rigid. Ionic compounds have really high melting points. So it's going to take a ton of heat to break this bond between ionic compounds. The reason is, again, this Coulombic attraction is holding them so tightly together or trying to keep them so closely bound together because there's all of this attraction that it's going to take a lot of energy to break that or overcome that attraction. So ionic compounds or formula units have really, really, really high melting points. To continue on, ionic compounds in a solid, these ions are locked in place. So ionic compounds in form of a solid, they're not good at conducting electricity because their ions aren't able to move around. But if you melt this ionic solid, if you melt an ionic compound that's in a solid state into a liquid state, then those ions are able to flow more freely, and then they will conduct electricity really, really well. You could also take an ionic compound or an ionic solid, and you could dissolve it in water, and then that would also get us to conduct electricity really well. Guys, I think we have, here we go, one more. So if we take an ionic compound and we dissolve it in water, we get this compound to break up into its ions. So here I see sodium, and then I see chlorine ions. So as I see these little atoms, they're moving around. They have the ability then to conduct an electric current because they have, like chlorine has this extra electron that's on it, so it can conduct electricity really, really well. They're able to move throughout this water and move the current along. Last thing, in terms of a property for an ionic compound, this really, I think, demonstrates how an ionic compound can break really, I think, pretty easily when you apply some type of extra force or external force. So here we have some type of crystal structure or crystal lattice. So I see that it's just a repeating unit. I have a plus charge, a minus, a plus, a minus, a plus, a minus, a plus, a minus. So it's just like this repeating structure over and over again. If for some reason it comes in contact with an external force, like I have a hammer here, I kind of knock it down. Look at, I have two positive charges now that are next to one another, and I have two negative charges that are now next to one another. Does two positives and two negatives, do they want to be next to one another? Do these two positives want to be by each other at all? No. Do these two negative charges want to be by each other at all? No. So it's going to split apart because of this repulsion force now. It's no longer this attractive force. Now they're going to repel each other. So that's why when we bring a hammer, if we add some type of external force to an ionic solid or a crystal structure, it will break really easily because now we've messed up that force of attraction between those ions. Guys, this gets us through our PowerPoint on ionic compounds and ionic bonding. Let me just give you an idea of what we're doing for next week. On Monday, we're going to have some practice naming ionic formulas and ionic compounds again. On Tuesday, I'm probably going to give you a little small quiz over naming them, and then we'll probably have one more day of practice naming just depending on how you guys feel. If not, you feel like you're doing well, then we'll move on to covalent bonds. So on Wednesday, Thursday, Friday, we will definitely be doing something with covalent bonding and also naming molecular formulas. And then before you leave for Thanksgiving break, we'll be playing Vesper Hold'em with different shapes and geometries of molecules. You'll also be doing a POGL activity sometime before Thanksgiving break as well, and we'll try to throw in a lab too. So just to give you an idea of where we're going, hopefully the day before you leave for Thanksgiving break, I'm hoping that we can have all of our bonding done, so then that way, whenever you come back, we'll immediately start on the mole, okay? So have a great weekend, and I will see you guys on Monday. Bye!